Hello, everyone, and thank you for joining us for today's session. My name is Danny, and I'm the event planner for the New York Reactor Space. Before we start, I have a few things to go over. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our audience and presenters. We encourage engagement in the chat, but please be mindful of your commentary, remain professional, and on topic. Useful links will be shared in the chat. The session is recorded and will be available on demand 24 to 48 hours on the Microsoft Reactor YouTube channel. Which brings us to today's session. It'll run for approximately 1 hour with time for questions throughout. I will now turn it over to our speaker for introductions.
Welcome everyone. Good morning, good evening, good afternoon. I am very much excited to have you all here today. So in this session, we'll explore how AI or agents understands the meaning using embeddings and vector similarity, and we'll break down the science behind semantic classification and see how it avoids hallucinations, recommendations, and AI reasoning. So let me introduce myself first. So I am a senior software engineer at Microsoft Redmond, Washington, and I have overall 10 plus years of work experience in software engineering field. I have worked on many .NET, C Sharp, and Java applications in my career, and particularly since last 2 years, I have been focusing on implementing co-pilot systems, agentic AI, and prompt engineering. So let's understand the agenda for our session today. So first we'll look at the real world challenges, like why Gen AI agents sometimes fail and what are the consequences after that. Next, we'll discuss about semantic classification. It's like how AI or agent understands the meaning beyond just words. Then we'll explore embeddings and vectors, which are the core foundation of making AI or agents much smarter. After that, we'll dive into vector similarity, specifically cosine similarity. It's the magic behind AI finding relevant information. We'll also talk about Azure AI Foundry and then hands-on coding session. We will deploy our model in Azure AI Foundry, and I will show you how to implement all of this in .NET C Sharp application. And finally, we'll wrap up with best practices, which will cover cost optimization, efficiency, and scaling AI applications. And after that, I will open the doors for any questions and answers. All right, so let's get started. Let's first understand what is this session about. And we'll start with a real world challenge that any enterprise face when building AI powered co-pilots or agents. So imagine a scenario that a company has an AI assistant or agent that retrieves data from multiple data sources. So it could be internal documents, APIs, and databases. And they are also powered by LLMs and models like GPT, Llama, and Gemini. Sounds great, right? But here is a problem. So what happens when the query is ambiguous? For example, let's say a user can ask, how should investment policies align with employee rights? So, does this query belong to finance and which deals with investments, or legal, which handles employee rights? So, if the system doesn't classify the questions correctly, here is what happens. First, hallucinations. So, the AI or agents may generate completely incorrect or misleading information. Second, inconsistent responses. So the asking same question twice may give different answers. Third, loss of trust. So users will stop relying on agents or AI because it doesn't provide accurate information. So this is the major issue because if AI retrieves wrong information, it can mislead users, even cause legal or financial risks. So what's the solution? The solution is proper semantic classification, and that's the session is about. And it will make sure that AI understands the context of a query before retrieving data. So let's explore how we can achieve this. So let's understand now what is semantic classification. So semantic classification basically helps AI or agents to understand the intent behind a query, not just through the keywords. It ensures that even if the different words are used, the AI correctly identifies what user is asking. So let's understand how does that work, right? So instead of just relying on keywords, we use the taxonomy concept here. And the taxonomy is nothing but it is grouping similar queries by their meanings. So in AI systems, we define like predefined categories. For example, it could be finance, HR, legal, learning, etc. And then we associate relevant keywords and embeddings with them. So this helps AI accurately classify queries and even when they are phrased differently. So let's take an example. So for example, user may ask, how do I apply for business loan or steps to secure company funding? So you can notice here is that both of the sentences are different in words, but they mean the same thing. They belong to finance category, right? And similarly, other examples like what's our vacation policy? How many paid leaves do we get? So again, here both of the sentences are different, but they belong to HR category. So this is how semantic classification helps grouping queries with similar intent together. All right, so now let's talk about vectors and embeddings. They are the key building blocks of any modern AI systems. So what are the embeddings, right? So embeddings are nothing but it's just a numerical representation of text or sentences, and they are mapping words, phrases, and even entire documents into high dimensional vector space. So instead of just treating words as just characters or simple keywords, embeddings capture meanings, relationships, and context in a structured way. So we have different AI models. They can generate embeddings with different dimensions. The higher the dimension is, the more information the model can encode. And let's look at the popular models. So first model is text embedding ADS002, and this model we will be also using in our code. So this model is developed by OpenAI team, and they have 1,536 dimensions. And there are also available models, open source models like BERT, developed by, it's available through TensorFlow, and also like the fast text, which is open source via Meta. They have a little bit lesser dimension, 768 and 300 dimensions. So each of these models transform text into vector of numbers and making it possible for AI to compare their meanings, even if the words are themselves are different. So let's take in two examples. So if we talk about stock market investment, so the embedding vectors can be got from 0.98, 0.12, or 0.76, and so on. And buying shares in a company, the vectors could be 0.87, 0.11, 0.78, etc. So this is about vectors and embeddings. It nothing but just like we are representing, like the text or sentences in a vector space. All right. So now let's understand vector similarities because we have now understanding of vectors. So remember back in high school or college when we learned about vectors and angles in geometry, right? So well, cosine similarity is basically exactly same, and it's an even extension of that, but in terms of languages and AI. So it's a mathematical way to measure how similar two vectors are, not by their size, but the angle between them. So just like in geometry where we measure angles, here we measure the direction of two text embeddings to understand how closely related they are. So why does this matter, right? Because it helps determine whether two pieces of text are conceptually similar, even if the exact words aren't the same. And uh, we will we will use this cosine similarity in our code in the demo. So we can now, achieve semantic similarity by first convert text into numbers, which are like vectors, and then calculate cosine similarity to see how words and phrases with similar meanings get mapped closer together in the space. And depending on the result, the AI agents can now compare queries, classify intent, and find relevant information efficiently. There are a lot of use cases you can achieve using cosine similarity. So if we look at the similar example that we just saw in the previous slide, take stock market investment and buying shares in a company. So if we take the cosine similarity between those two vectors, it is coming out as 0.998, which is like huge, which means that AI recognized that these two phrases are almost identical in their meaning. Instead of relying just exact keyword matches, cosine similarity basically helps agents to find most relevant information. Again, so if you are more interested in diving deeper into how semantic classification works, then how models generate embeddings and how they even decide number of dimensions, I have written a detailed article on Medium platform. You can check it out, and the link is already in the description. Okay, so before now we go to the demo and the code, I would like to explain a little bit about Azure AI Foundry, because as I was just mentioning before, like we will deploy our model in Azure AI Foundry platform, and then we will use that model inside our code. So Azure AI Foundry is nothing but it's a AI platform developed by Microsoft and Azure team, and it's particularly designed for building, training, and deploying custom AI models. And it also provides end-to-end solutions with even other Azure services as well. There are many good features available for Azure AI Foundry. For example, it supports multiple AI use cases like NLP, computer vision, predictive analysis, then built-in tools for model management. You can even like monitor, you can version your model for the continuous improvement. And since it is using Azure infrastructure, it's like very much scalable and performant for any AI execution workflow. There are also some other features like Chat Playground, where you can play with prompt instructions and craft a good prompt instructions for your agent and use cases. So, if you would like to learn more about Azure AI Foundry and Chat Playground, I have already taken a session on Microsoft Reactor back in December on building how to build agents using Azure OpenAI. You can watch that and learn that about that, and you can even find the link in the description. All right, so now let's go to the hands-on implementation and the C Sharp .NET code, where I will be showing you how we can achieve all of this in the code. So before going into .NET C Sharp, we will try to deploy our model in Azure AI Foundry. So I'll give a brief overview about Azure AI Foundry. So let's go to the Azure portal. So this is the Azure portal, and I have already created Azure OpenAI service. It's named as Adit Azure OpenAI service, and you can see all the metadata here. And when you click on this Go to Azure AI Foundry portal, it will open the tab, and you will see it will land here. This is the home page for Azure AI Foundry, where you will see all the metadata for the your subscription, and then pre-pricing tier, location, Azure OpenAI endpoints, etc. And here, let's go to deployments window. So this is the page for deployment tab, and you will see that if you want to deploy the model, you can just click on this plus button, and you can also deploy base model. Also, you can deploy your fine-tuned model. So if you click on the deploy base model, this will give you the list of all available models, supported models in Azure AI Foundry. So you can also search the model. So for our demo, we will be using text embedding ADS002, as I was just mentioning before. And this is developed by OpenAI team. So since I already have this model deployed, we will be using the same model. And once you deploy the model, you will see all the metadata, for example, model version, state, then content filter, deployment type, capacity, rate limit, etc. Okay, so now we have our model already deployed in Azure AI Foundry. Let's use this model inside our code. So let's go to the code. So here I have already created a very basic console C# application in .NET, and I have my program file which has a public static void main function, and I have also created a very basic template for this demo. So let's understand the goal here first. So our goal is we will try to give user input, and we will try to stitch all the learnings together. For example, semantic classification, cosine similarity, and taxonomy, and embeddings and vectors. And at the end, once the code runs, it will try to give us the output, and it will tell us that the user input is related to which category. All right. So for any now embedding based classification, there is a generic algorithm that we need to follow. So this is the algorithm. So before jump into the code, let's try to understand this algorithm step by step, and then we can implement that, right? So in the algorithm, first step is we need to define sample category taxonomy. So as we just saw in the slide, we need to define pre-defined categories, for example, finance, HR, and legal or learning, etc. And we need to, after defining categories, we have to use that taxonomy to generate the embeddings. So how to define that, what data structure we need to use in the code, I'll just show you in the bit. But our first step is like we need to define sample category taxonomy. All right. Now, once we have defined our sample category taxonomy, we will try to use the deployed model from Azure AI Foundry, and we will try to generate embedding vectors for all those four predefined categories. So this is our second step. And third step, like for just visual representation, we will also generate the text files for all those taxonomy categories, and I will show you how the vectors will look like. Fourth step is like once we have the vectors generated for taxonomy, we will try to generate now vectors for user input, because now we need to compare and we need to calculate cosine similarities between the user input and the taxonomy vectors, and so that will be useful. So that we will do in step number 5. So calculate cosine similarities between input vectors and all generated embeddings. So we will try to calculate cosine similarity again user input against all four predefined categories. And at the end, like whichever similarity is the highest one, so cosine similarity value which is like greater, then we will try to output that, and we can safely say that like user input is relevant to that particular category. Okay, so now we have now good understanding about algorithm. Now let's go to each step one by one, and then we'll try to implement that. So for first step, the taxonomy step. So here, we are defining 4 different categories, which is finance, HR, legal, and learning. And I am using a dictionary data structure because as a key, we are putting the taxonomy keys and category, and the values we are putting all the comma separated values which are associated with that particular category. So if you are using Java, you can use hash map. If you are using any other language, then you can use any key value pair type of data structure. So here we are using C#, so I'm using a dictionary. So this is the first step, like we have defined our sample category taxonomy. Okay, now let's go to our step 2. So our step 2 is now we need to generate embedding vectors for all these 4 categories defined, right? And as I was mentioning before, like we will be using Azure AI Foundry, and here we will be using Azure Open AI Client class, and which generally accepts like two inputs, endpoint and key, right? So let's try to get this details. So you can find this information from your Azure AI Foundry portal. So let's go to home and let's copy this. So this is the Azure OpenAI service endpoint. So let's copy this and let's paste it here. Now for the key, I already have created the configuration class. So let's use that configuration.azure OpenAI API key. And the deployment name, let's try to get a deployment name. So let's go to Azure AI Foundry and go to this deployments, and whatever model that we have deployed, like we need to give them deployment name. So right now we are using text embedding ADS002. So let's copy this and let's paste it here. So you need to use exactly similar string for that. Okay, so with this three information, we have now our client object created. Okay, so now once like we will use this Azure Open AI client object and we'll try to get the embeddings. And now we are storing that result inside the dictionary data structure only. So that data structure is a dictionary of string and float, right? And because string, we will be using the same category that we are defining here, finance, HR, legal, or learning. And the values would be float array. So if you remember back in slide, like when I was telling, vectors are like high dimensional space. So here the float array data structure is the best structure to use that. So let's define the dictionary of string and float for the category embeddings result. And since we need to calculate this embeddings for all four values, we'll try to use for each loop, right? And then we will be keeping the key as is, whatever we are finding in taxonomy. And now let's try to get embedding function. So this method, I have just created a signature for it, which accepts three things: client, deployment name, and text, right? And let's try to now implement that. So let's remove this, and also let's remove this. So here, like we will be try to use Azure OpenAI client object, and then we will try to create the embedding client. So let's try to create that variable embedding client equals to client dot get embedding client. And if you look at here, like it accepts deployment name as a argument. So let's pass the deployment name. Okay. So we will use this embedding client to get the result. So let's store that into result variable. Variable result equals to embedding client dot generate embedding. And here we are passing the text. Text is nothing but the comma separated values in the dictionary. So let's pass the text here. Okay. So one thing you can notice here is that this result is an object of client result and open AI embeddings, right? But we need to return the float array. So that means we need to convert that result into float array. So let's do that. Return result dot value dot two floats dot two array. Okay. So this will convert our result into the float array. All right. So we have now our get embedding function implemented. So basically this function will help us give all the embedding vectors for our taxonomy. So at this point, let's try to run this solution and see like how does this work. Let me run this solution. It's building. Let's wait for a few more seconds. It's still building. Okay, now it has opened. Let me show you this. So it is asking us to generate embedding vectors. Let's say yes. So now it is going into Azure OpenAI service, and then it is trying to generate embeddings using the model that we have deployed, right? So it has generated now four different embedding vectors for four different categories: finance, HR, legal, and learning, because they are available in our taxonomy. Let's close this. And you can also observe here is that like there are four different files generated. So let's try to open that. So this is the finance category, and it has generated embedding vectors like the dimension. If you remember, like the dimension was like in more than 1,000. So it has generated like 1,000 values in this array. Similarly for HR category, right? Learning, and then legal. So it has now generated vectors for all predefined categories from our taxonomy. Okay, so now let's go back to our program.cs class. So at this point, we have our second step completed. We have the taxonomy. We also completed our third step because we just saw the embedding vectors from the text file. Now, our fourth step is, as I was mentioning before, like we need to generate embedding vectors for the user input. So we will try to get the input from user from console application, and we will try to generate the vectors for that user input. Okay, let's do that. So I already have that code available. So if you look at this, like we can use the same get embedding function to generate even user input embeddings because uh, we just need to pass input text instead of comma separated values, right? So this code will try to generate vectors for user input. Okay, our fourth step is now completed. Now, after we have all the vectors available, our final step would be like we need to calculate cosine similarities, and then we need to compare those cosine similarity among each other, so we can know that which is the higher cosine similarity. So that exactly thing we will do in step number 5 and 6. We will try to like generate cosine similarity between user input against all of the vectors that we received from the taxonomy. So I have created this function signature get best matching category, which will try to output the most relevant category for the user input. So it accepts input embeddings, which is like input embeddings are nothing but it is the embeddings for user input. And it accepts the dictionary as well, because we would require to compare those input embeddings with the vectors, and we need to calculate the cosine similarity. So for that, we will need best category as a variable, and we are going to output that. And high similarity, we need to also keep a track of one variable, because we will try to, calculate cosine similarity, and we need to also identify that which is the highest similarity among all these four. So let's try to implement that. Okay. So let's try to use for each loop. So for each and variable category, here it would be category embeddings, and let's try to, just for easy understanding, let's tell it as a taxonomy, variable taxonomy in category embeddings. And let's try to now calculate the cosine similarity. So let's try double similarity equals to cosine similarity, and then we will pass. So cosine similarity function signature is also created, like it accepts two vectors, vector A and vector B. So here our vector A would be input embedding, and our vector B would be the dictionary value. So category embeddings dot values, right? Sorry, not category embeddings, but since we are using taxonomy, so taxonomy dot value. Okay. Okay, so now like we need to keep a track of highest similarity. So we can just put a condition: if similarity is greater than highest similarity, then we will just update similarity equals to highest similarity. And then we also need to output the best category. So we will take that key and output that. So it will be best category equals to taxonomy dot key, and we will return that best category. So here, like just for visual representation, we will also try to output the cosine similarity. So we will see that in console. So let's do that. So let's see console dot write line, and let's output that cosine similarity with, and then we will do taxonomy dot key, and we will append similarity. Okay, so this will give us the idea about like what was the similarity, cosine similarity value for all those four categories. All right, so now we have our this signature function is already created. Now we will, the last step is we will try to calculate cosine similarity. So let's try to go that function. So this is like cosine similarity. So this is the formula for cosine similarity. If you want to calculate between two vectors, then you need to take a dot product of two vectors divided by magnitude of A and magnitude of B. And if you convert that into math formula, it will be like summation of A dot B, and for all the dimensions divided by square root of A star A and square root of B star B. Okay, so let's try to do that. So we need three variables: dot product, magnitude of A, and magnitude of B. Let's try to implement that. So let's see dot product plus equals to vector A of, so we need to go for all the dimensions. So let's try to use loop here. So for int I equals to 0, I less than any vector length I plus plus, and dot product plus equals to vector A of I star vector B of I. And our, let's also calculate the magnitude as well. So the magnitude will be magnitude A plus equals to vector A of I star vector A of I. And similarly for magnitude of B, let's do that. Let's change it to B instead of A. Okay. And now let's try to return the output. So return dot product divided by uh, math dot square root of magnitude of A star math dot square root of magnitude of B. All right, so we have now also cosine similarity completed, and it will calculate cosine similarity between those two vectors, right? And let's try to see, we have completed all the things. So here we are returning best category, and then here we need to return the best match instead of empty strings. Let's do that. All right, so we have now all 5 steps or 6 steps completed. Now let's try to run this. Okay, let's run this. It's building. It's, let's wait for more seconds. Okay, now it's running. So now it is asking me that do you just want to generate embedding vectors? I'm saying no. So now it is asking us to provide input text to classify. So we can take the similar question that we just saw in the slide. So we can, let's ask what are the best strategies for investing into stock market, right? Okay, so let's wait for a minute because it is trying to compare embeddings and all those things, right? So now here you can see that like user wants to learn about best strategies, right? So he or she wants to understand the idea, and that's why if you see the category is like it has calculated the similarity 0.81, 0.73, 0.76, I think we are probably giving the wrong output in the code. But if you see, the similarity is the higher similarity, which is the finance similarity. So which is trying to output that best match category, right? So we have a bug in the code. Let's try to fix that. Uh, let's try to fix that. So here we are trying to, so this won't be in the loop. Let's remove this. And here we need to output the similarity. So this is in the loop. So let's output, keep that outside of the loop. Okay, give me 1 second. Let me fix this. Okay, similarity. Uh, so we are calculating similarity here, and taxonomy dot key, and we are appending similarity. So similarity is the highest similarity. Then we are outputting that, and here we are returning best category. Uh, Somewhere the problem is there. I need to debug the code. But if you, let's try to look at the other example, and let's look at only the values and see which is the highest value. So the solution is running, and let's try to do that. Let's try to generate embedding vectors, and let's ask question. So here let's ask, let's tell no first, because we need to input. And then how many paid leads do employee get in a year? So let's try to run this code. Okay, so somewhere it's a bug, so you can just ignore this, but you can look at the similarity, which is like the highest similarity is 0.76 among all those three. So this category is relevant to HR. So in this way, you can, like, for any agents or AI, you can, before even going into APIs or, like databases or something, you can ground your data sources accordingly. And then you can first output the category. And depending on the categories, you can, only restrict your search from that category. So you will completely avoid your hallucinations, and you will get the accurate responses. All right. So this is about the code and the demo. Now I have a couple of more slides to cover. Let's go back to the deck, and let's go to our almost final slide. So this is my favorite slide. It is talking about best practices. So uh, like, it will talk about how we can reduce API costs and optimize storage and improve retrieval speed, while working with embeddings and semantic classification. So there are multiple techniques, like in, the industry experts do. For example, it will you will like lower API and compute cost by, batch processing of queries. You can also use serverless options like Azure functions. You can also like cache your embeddings and taxonomy. For example, instead of just calculating that as a runtime, you can pre-store that. You can use like cache for Redis, in-memory cache. There are also other techniques, like you can even reduce storage costs. Like, for example, you can use like, compressed or lower dimensional embeddings depending on your requirement. There are multiple vector databases available. For example, FAISS, which is like Facebook AI Similarity Search, which is also cost efficient. And you can also apply like hybrid embedding approach. Like you can combine pre-training embeddings with some, common tasks, but the custom trained embeddings for like particularly domain specific tasks. And you can also adjust dimensionality for a balance between cost and performance. So there are many techniques you can apply to have a best practice and lower the cost down for the classification and recommendations. Okay, so these are my resources I have prepared my session from. I have taken few slides from Azure, like documentation, OpenAI documentation, .NET documentation, and on the profile and blog side, like I regularly contribute to Medium articles, and you can follow me at the red shade Adit, and you can also follow me on the LinkedIn. My ID is Adit Sheth, and I also contribute to open source. Projects you and on GitHub, so you can also follow me on the GitHub. All right, so this is all about the session. Now I'm opening doors for any questions and answers. Please feel free to ask any questions. Thank you so much. Okay, so let's see what questions we have. Okay, so does it do semantic ranking? Can you please provide more detail about that? So it will also provide, oh, I understood that. So it will also provide semantic ranking because you have a flexibility to, even pre-train your model, particularly for semantic classification. So this will be definitely possible. Yes. Okay, any other questions? Okay, if we don't have any more questions, then okay, any other questions? So far, the resources flashed on how to hit log. I'm not understanding, Dick. Okay, but if you have more questions, obviously, then after this session, the feedback form will be shared, and you can write your questions, and you can reach out to me. I would be happy to answer all those questions. But thank you so much for attending the session. Let's make our AI community much stronger. That will be awesome for all of us. Thank you so much. Thank you. Bye.